Cool. Okay, so welcome back. I hope everyone has had a chance to look at and play around with some of the exercises. I was kind of hoping that today wouldn't be just me talking, but I do have stuff to talk about in the exercises if no one else wants to share things I've played around with. I guess my hope is that we turn this into more of a group thing on the off week. So we'll have a host. Obviously, we've talked about we'll have a host that brings up some topic and can go through some of the fundamentals, introduce stuff. But then 2 weeks later, it'd be nice if other people could share stuff they've worked on or played around with, and make this a sort of a group exploratory thing. If people haven't, that's fine. I can talk. And there's one thing at least I want to go through and show. And I'll begin with that, and then maybe I'll ask and see if anyone else wants to share things they played around with. Okay, so maybe first, or maybe it's a bit hard because some of you are in a big room, but like if you can use the raise hands thing to say if you actually played around with any of the code at all in the last 2 weeks. Or I can play a chime to ask for raised hands. That's nobody, I think. Okay. Oh, we got one, maybe.
We had a couple of people here do it, Jay.
Pardon?
We had a couple people.
Got a couple of people.
Yeah.
Okay, I'll share my screen and bring up. So I pushed an update to the GitHub. Now, Matt mentioned that he'll reorganize this a little bit. For now, what I've just done is I created a subdirectory which just says mini workshops, and for each mini workshop we can have a folder and have materials for that folder. And we will keep recording these, and the recordings will be available. I'll paste the links into each of the little mini workshop pages. Okay.
Sorry, Jay.
The wrong.
The code for this notebook, whereabouts is this? Is this on the?
All right. Well, let's just go to the page and we can open it from there. Okay, so this is the page we were working from for the workshop we did in February, but it's meant to be general, so it's on Matt's page, mjg-phys, and then it's /cdm-computing-subgroup. And I can paste this into the thing in case. How do I get to the chat easily from here?
Yeah, thanks.
Okay, so yeah, so as I was saying, I started this mini workshops, and maybe we'll reorganize this and put all the February workshop material into one folder. So open up this notebook. And open it in Colab unless you've already got it working on your own machine. Okay. Okay, so last week we went through all of this. So there were no exercises from this initial section just on generating random variables. And then we launched into doing something useful. So we started with this calculation of pi just from random numbers by throwing random points at this circle and looking at the ratio of the areas. And then as an exercise, I invited you to write a function that would calculate the value of pi using this method, but for a given number of points. So I sort of did things very manually here. But of course, you can easily imagine writing this into a function. And so the simple one I did here was just use some function called pi approximation that asks for a number of points that will define how good the approximation is. And then it just goes through the calculation. So we throw out random points in X and Y, and then we count the number of points that lie within the unit circle. And then we return number of points in the circle divided by the total number of points times 4, which is going to be our approximation of pi. And then this thing here just makes sure you can call it with a numpy array as the argument. So now in this part, we're just going to do that calculation for a range of values. So we'll do it for stepping up in orders of magnitude from 10 up to 10 million. And then this will actually just do it. So let's run this. It doesn't take too long going up to 10 million points. I'm going to close the door because it's a bit loud here. And now we can plot how that, so I invited then as part of the exercise to plot how that approximation goes as a function of the number of samples. So here across x-axis, how many samples we did. And then this is showing how well our number approximates pi. So obviously pi is along here and it jumps around a few times and then pretty quickly converges, and then we can't even see how far away it is from the actual value of pi. So just to look at that in another way, we can plot the fractional error as a function of the number of points. So here we just subtract off the actual value of pi, divide by pi, and we see it jumping around but heading down. And so this is like telling us that we've got 1 decimal, 2 decimal, 3 decimal, 4 decimal points of accuracy by the time we get to 10 million points. And what I've superimposed that with is 1 over root n. And this shows up all the time in Monte Carlo, that your accuracy scales as 1 over square root of n. So yeah, as you increase the number of points, you get better. And you can ask why. Why does that happen? So let's just have a look at the distribution of the pi values we would get for taking our calculation with 1,000 as the number of points that we throw. So we're gonna just like look at right here. So with 1,000 samples, we can ask what is the distribution. So this is just one example. What's the distribution that we get of pi values approximation when we're just using 1,000 points? So we'll do that approximation of 1,000 points 10,000 times. So actually, let's just do it. And I did this because that's the equivalent of doing 10 to the 7. So it takes about 20 seconds. You don't want to do much longer than that. And then we're going to build a histogram of our pi approximations with only 1,000 samples. Okay, 18 seconds. Okay, so here it is. So nicely, as you would expect, this distribution has its own mean around pi, but it also has some width. And that width depends on how many samples you have. So as you increase the number of samples, if you did this again, but with n of 10,000, then this will get sharper and sharper and sharper. And yeah, so this looks a lot like a normal distribution, and that is because it is. And that's due to the central limit theorem. So I'd invite you to go and look at that. I had originally put in a Wikipedia link here, but it's much better explained, I think, visually on this YouTube channel, if you haven't done it before. So the central limit theorem states that the sample distribution, so this 1,000 samples taken out of the true distribution will have a standard deviation that goes as 1 over root n. And that is really the principle behind what makes these Monte Carlo methods work. And lets you be able to set an error for a given number of samples. So if you already know a priori that you want a certain error, then you can do some Monte Carlo estimate and you can stop after some number, knowing that you're actually converging on the true actual value. Like here, we know what the true actual value is, so we can test and see that 10 to the 4 is sort of sufficient if you're only interested in percent level accuracy. But for many of the integrals that we go and do, we don't know what the true value is. But so it's important to know how these things scale with n, so that you can get robust error estimates and trust them. Okay, do we have any questions, comments on that? No. Okay. So we can move on. In this next section, we were doing random sampling from distribution. So we wanted to be able to reproduce and give random samples from any given distribution. And we started with this normal distribution using what we called the guess and check method. So again, if you throw random points at this space, but then only keep the points that are below the curve, then those points below the curve will follow the distribution. And so you can get a quick approximation of distribution. And the first exercise, I invited you just to write a function which would take a given function and give you back some random samples in that function. So here I wrote a function that had x min and x max. So you need to tell me what is the minimum, maximum x values you want your points to lie between. You pass in a function, number of points you want, and then optionally what the maximum is. If you don't pass in what the maximum is, this is so that, like, when I threw these points here, you need to throw them above where this peak is. Otherwise, you're going to clip the distribution and you won't represent the true distribution. And this is sort of also assuming you knew what the minimum value was, that it goes to 0 somewhere. In practice, what I've done to take care of that is that you can just randomly sample the whole function across x min to x max and then work out what the maximum is, y max, and what y min is, and then use that to scale your y random numbers. So here, it's sort of a more optimized version where you'll throw all these random points in x, and then you only throw random points in y between the minimum value you've sampled and the maximum value that you sample randomly in the function. Now, that can sort of work only if you've sampled enough, so that you've got enough points that you've probably sampled somewhere near the maximum. That's not going to work well in many dimensions, for example. So we can run that. And then, yeah, and then so then you just have to loop over all the samples you've taken to see which ones to keep. So you do that, and okay, I didn't run something up here. Just meant to run everything as I go. Let's try that again. So, okay, so now having done that, we can run the example. Okay, so there you go. So here what I did was I defined a test function, which was just the normal distribution, and then calculate some samples using our own function. So you should, in principle, be able to put in any function here. And then you'll get random samples according to that function. Now, there's no checks on whether this is a well-behaved function. So It's sort of assuming that the user is putting in something that makes sense, the distribution. And there's probably plenty of edge cases there that this would trip up on. All right, so a more useful version of that. So like we discussed, this is pretty slow because you throw n points and then you keep a fraction of the points that's proportional to sort of the area below this curve. So it's really not good for sampling out in the tails, and it's just generally inefficient. So we looked at inverse transform sampling, where I was just saying, if we've already got random samples between 0 and 1, we should be able to just stretch them out into some way into this distribution. And we do that using the inverse CDF. So I made this plot to try and illustrate how you transform this uniform distribution into, by passing it through the inverse CDF, you transform it into the normal distribution, or the distribution that this inverse CDF corresponds to. So, and then as an exercise, I invite you to write your own function that would do this. You need to write your own class because you don't want to have to reproduce inverse CDF every time you call the function. So you need to create a class which stores the inverse CDF that you calculate and then can give you back random numbers. So this is how this works. So we have a class called inverse transform generator. And when you want to make random samples from a distribution, then you're going to create an object of this class. And when you create it, you need to initialize it. So you pass it a function, and then the x min, x max you want to sample between. And this number of points is not the number of random points. This is the number of points you want to start to generate the initial inverse CDF. So the more points you put in here, the more accurate your inverse CDF will be. And so the better your number generator will be. But here I've just stuck it at 100 just to be good enough for the example. But in practice, you'd want this to be higher. So that's just like the default argument, but you can change it. And so what you need to do is, and we did this up above, is you create some space, some grid of values in the x direction, and then calculate the y values for the function. Now, we need to compute what the CDF is. So here I do that I'm just using the built-in trapezoidal integration. So this little line of code just integrates from the minimum x value up to the y value. Sorry, up to some other x value. And then it stores this with the y values, stores the result of the integration in a new array. And so you do that by looping over the whole thing. So if that's not clear, I think like these sort of things, like it's hard to go through a line of code that I've written. I could have written this more clearly, but I think if you want to understand this better, you should just write your own version of this function. And that was sort of why I put these exercises in. And it will become more clear to you if it doesn't now. Now, one thing is that when you've passed in this function, if it's not normalized, then it won't act as a CDF. So I just divide out the value of the CDF by the last value, which means when you've integrated the whole function from x min to x max. So that'll make sure that this function that you produce will be normalized. And then the last step, we just need to create an interpolation object so that this can act as a function. So we've calculated the CDF values from x min to x max, and we have this array. And now we just set up an interpolation object, which has those CDF values, and then the x values. So what are these are flipped. So your x direction in this interpolation object are the CDF values, and that is how we turn this into the inverse CDF. So it's a very quick way to get the inverse function. Just evaluate it at a grid, and then you swap your x and your y values. Okay, so now that gets stored in the object as inverse func. So you've created an object, and all that's done when you initialize it is it does this inverse CDF calculation and stores it. So now we need to define a function that you can access in that object, which will give you samples. And there we set it up just with only one argument, and that is how many points you want it to return. So it just returns the inverse function, and then you pass it some random number between 0 and 1. So then that does, so what's happened is you've calculated this, and now you can just pass in a random number, and then it will give back some in the distribution. So, okay, so we've defined those. And now let's do an example. So I'm going to be boring and keep doing the same test function, which is what we used before. That's just the normal distribution. I'll evaluate it from -5 to 5. And I'm going to say, let's do 1,000 points, so it's reasonably accurate. And then after that's been created, we'll generate some samples from that distribution. So this is my object that I've created, and now I have this function that we can access, get samples, and I'm saying, give me 1,000 samples. And then we're going to plot a histogram and also sort of the analytic version that we'd done before. Okay, so that worked well. And if you tested to see how fast this is, after setting it up once, this will be a much faster way to get points from the distribution. Any questions on this one? Nope. Comments? Again, I haven't written this to like make sure that it's this is good code that's going to handle every situation that you throw at it. So you might want to play around with that and think about what some edge cases are. Okay. Now the last version of sampling we did was using Markov chain Monte Carlo, because like I said, the above works well in 1D, but it doesn't work once we go into multiple dimensions. So we set up the Metropolis Hastings algorithm to do a random walk, well, a pseudo-random walk through some function. And then, so this was just our initial random walk that was unconstrained. And then we did a longer one, and I said we should, let's just constrain it to a box. And so last week, actually, we did this, and someone pointed out how the edges didn't look great. And I sort of was saying how you need to choose your step sizes and so on, so that you sample the space well. And then someone pointed out that you could do this well if you just imposed periodic boundary. So what I've done here, I did that. I went and put the periodic boundary conditions in to show that that worked. And that is actually a much better idea of how to do that, this version, where you want to sample uniformly from a square. Okay, so this was just introducing what the Metropolis Hastings actually is. So now, instead of just taking every random step, we propose a step, and then we only take a step if the ratio of the function at that new point divided by the one where we were is greater than some random number that we draw. So if this is greater than 1, if we're always stepping uphill in the function to a greater point, then this will always be greater than 1, and we'll always take that step. If it's less than 1, then there's only some probability that we take the step down. And as you're sort of stepping further downhill in the function, there's less and less likely chance that you're going to take that step. And just with that simple rule, we showed that you're able to sample from a distribution, and your random walks would end up following some distribution. So let's run that to make sure I didn't skip something that I need to run. The other thing I had sort of talked about a little bit was choosing these random steps and how there was some importance in the step size. I played around with this. I found that like if you take your step sizes to be really small, it's sort of counterintuitive, but if the step size is way too small, it more quickly didn't approximate the distribution. And you can sort of think of that as if the step size is really small, then you're not going very far. And so this ratio tends to be very close to 1, which means that in the case where you're stepping downhill, that will be close to 1, and there's still like a much higher probability that you'll step downhill, versus you'll still step uphill with greater than 1 probability. But say like you're in this function and you're sampling random directions, you're sort of much more likely to step in a direction which is downhill from any point, because there's only one direction which is uphill. And so if you set this too small and that ratio ends up being quite close to 1 a lot of the time, then you'll take a lot of steps downhill and you won't sample the distribution very well. So I thought that was kind of interesting. I also played around with if you take steps just from a uniform distribution rather than normally distributed, it doesn't change things much, except the step size. This is effectively like it has a larger step size, because like so the average step size when you're just sampling from a uniform distribution is much larger than if you're just sampling from a normal distribution. So I put in this, I rewrote this so that now at each iteration, this is your proposed step. So your random step is where you currently are plus some step that you take. And now that's a function so that you can choose the distribution. It's easy to sort of rewrite what distribution you want it. And you could even have that as an argument if you wanted to write this up as a function. The type of stepping that you do at each point. So we run that, and then we got this plot. Yes, yes.
I mean, do you still sample correctly, no matter what type of step size or step like?
No, so that's what I was trying to say. And we can do this. If you choose this to be really small,
yeah.
Whoops, I did not mean to. I need to comment that out. Okay, it didn't care that there were 2 return things. It just returned the first one. So now this is with a really small step size. So look at that.
Yeah. Yeah, so that's impacting convergence. But I mean, if you ran for like a very, very, very long time, would that still converge to the correct distribution?
I don't know. I don't think it will necessarily. I think there is some tipping point where, because you're relying on this sort of mirroring the probability that you'll step uphill. Like, and again, like if you do it too, yeah, I'm not 100% on the, like, if there's a mathematical proof that would say this would eventually converge, but I don't think so.
Okay.
But I'm definitely not sure on that.
I think it also depends on the function, right? For just a 2D Gaussian, you for sure converge at some point, but if you have something with a lot of local minima maxima, you might get stuck somewhere.
Oh yeah, for sure. And right. Yeah, with the simplest function, especially in a Gaussian, you could imagine that it much more easily converges for a Gaussian.
Yeah, I mean, my experience of this is obviously you want to avoid that sort of situation, right? But yeah. I mean, it's often the case where if you also step too big, you won't necessarily step the tails or whatever. So yeah, and then always the question, right? Well, how do you know? Like, you can throw more computer at it, but at what point, how do you know you're correctly sampling the posterior or whatever?
Yeah, I'm not really familiar with like tests that you would do, but there's sort of general sanity checks of like, But I think you can do like auto correlations and things and have a look, and you can see that there are certain things that the distribution's not reproducing something that's well annealed. I have not really dug into the different methods there.
Okay.
Okay, so I put it with a very large step size and it was still fine. It could go even bigger, but I guess 5 is still the size of the distribution. The other thing that I played around with, I don't think I made any plots of it. I was just convincing myself. Did I put it in the exercise? No, I didn't. If you sort of think about like what is happening when you take these random points. So this is a step, it's a random step in a square. And the random normal is you're taking random points, and it's sort of, if you look at them, they sort of end up in a circle. And if you think about the direction that you sample, then the directions in a square are much, there's more points along the diagonal because there's just more area there. So when you sample randomly from a square, you bias like the 45-degree angles out of the square. You're sort of much more likely to step in those directions. When you randomly sample with normal distributions in 2 dimensions, say like you'll randomly sample every angle. So that's sort of like it's that's just an argument for saying using normal distributions as you're stepping is an easy way to make sure you're not biasing yourself in a given direction. And yeah, you can just make a histogram to convince yourself of that, of what the angle is, what angle you're stepping in, and that it's biased with this distribution. Okay, this is taking a long time to converge with a step size of 10. Or not even converge, just generate the points.
Okay, so you mentioned it's going to be better to sample with the normal distribution just so you don't bias the angle. So would this be equivalent if you were to randomly generate polar coordinates and sample that way?
Yeah, so you could do that. Yeah. Yeah, so that is a common thing. If you're interested in actually randomly generating directions, which I've had to do before, then yeah, you want to use coordinate system so that you get random directions. Yeah, I'm just going to stop this. I don't know how long it's going to take. Okay, so I set an exercise saying to check that this actually reproduces the distribution because we didn't do that. So I need to actually run this with a reasonable step size. And yeah, so the step size also depends on the distribution that you're using, obviously.
So, I mean, just to comment on that too, I guess, I guess there are situations where a normal distribution isn't, I mean, this is like a prior almost, right? Like on what you think is it? I mean, is it like that? Like, is it like some, you kind of expect that it's going to be, if you had a proposal distribution that perfectly matched the final distribution, would that be the best convergence?
Quite possibly. That sounds right. But I don't know, because the proposal distribution is about the step, and that's dependent on where you are. So I don't know if having it exactly matched is the optimal. I don't know,
I guess I'm just wondering if there's cases where the normal distribution would be unsuitable or right.
Yeah, maybe not.
Like, in my experience, right, that I've used this for like fitting, and there's not always the case, right, with a given fit parameter, right, that you want a normally distributed thing, but then maybe the sampling is different, right? So
Yeah, no, I mean, so like, I think it's a commonly used thing because of this property that even in whatever n dimensions, it samples equally from every direction.
yeah,
As long as you have the same step size in every direction. But yeah, like I don't necessarily think it's optimal for everything, but it is a fairly unbiased version. Yeah, I think that's I'm gonna go and read about that. It's interesting. So this is now just checking. That was the first part of the exercise. Just check that this is actually giving us a normal distribution. So that's the analytic result. And yeah, like I do this just to sort of motivate that it's looking correct, but this is like that's totally, the plot is just showing that it works by eye. So here I calculate the mean and the standard deviations to check. Now that gives us within a few percent the mean and the standard deviation. This was running with a much different step size. So let's go to what I thought was a more optimal step size and distribution, and we'll see, you can just see how that changes. So yeah, by eye they kind of look just as good, but do these end up any better? Yeah, I mean they're about within 1% now. So yeah, this is just something you can play with, and you can also check the higher moments to see that you actually are getting the distribution that you expect. Yeah, now so the second part of the problem was implement this Metropolis Hastings on a 3D multivariate normal distribution. And that was just to make it a bit more interesting than just something that breaks down into a problem of two independent dimensions. So here you can import the multivariate normal from SciPy. And so now we just need to put everything into 3 dimensions. And I've defined a covariance matrix here that I just sort of randomly played around with, get something that was different. And I put the means away from 0. So we'd also have that as a different example. Now we'll sample that with 10,000 points. Okay. And so that's what it looks like. So yeah, the means now are offset. And we've got some covariance here. It's not just a standard normal distribution. And now you can actually see that because we started at 0, 0, we have this initial part of the random walk where we're nowhere near the maxima of the distribution. And so it takes some time to find its way there. And that's why you can use these also as a way to find maxima. These random walks, pseudo-random walks. So to actually make sure that we're properly sampling this distribution, we should have thrown out some number here. So I talked about doing burn-in last time, but not that we needed to. So if we throw out the first, say, I don't know, 50 to 100 points, that'll make sure that you've gotten rid of this initial tail that you would never expect to sample this far away from the distribution. So yeah, you should throw away all of these, and then the rest should follow the distribution. Do we have any questions or comments on that one?
Just a comment that in practice, it's helpful to make like a trace plot. I don't know if you talked about that in the last week, but I mean, to sort of plot the value over time, or value as a function of samples, and it should converge to something that, you know, is about a mean.
So what was the thing you plot?
So you can plot each of, there's 2 parameters here, right? So you can, rather than histogram, you can plot them as a function of sample number. And
right.
they'll start you know, at 0, 0 and converge to some value and sort of fluctuate about that value.
Yeah. So
And it's I don't know what there must be some nice statistically good way of determining once it's, you know, reached a stable distribution. But I don't know what it is, because in practice what I do is kind of look at it and say, well, it looks like it's stabilized, right?
exactly.
That's the amount that I throw away.
That looks roughly like I expect. It's
Yeah.
behaving as I expect. But we can do that plot. So what do we want? We want this is scatter plot. Or you want it just as a function of the number of steps. Right, did I even go all the way?
My values and the X values would be implicit.
No, I said I didn't store this. So I need to store it. Or I can just evaluate it for each step. Don't know. This is going to want to take. What's the best way to do this? That work? Okay. I just want something like, how do I get, is it range?
You can do that. You can also just give it the Y values.
Just
And
give
then
it-
it'll just
give it the first array, it should be fine, right?
Okay, it knows. Just give it one array, it'll give you, okay.
Yeah.
That's not easy to see. So can we just take first, say,
is F vals 2D there? Is it?
1,000 points?
Right.
Still way too many. Yeah, it's not very obvious in this one that we're converging to some value. But this is what you meant, right? Just look at how the function evaluates over time.
Yeah, each parameter, the value of each parameter. So you've got the histograms. I don't know if you've got the,
Maybe.
so whatever is put in that histogram, you can plot that as a function of sample number.
I thought you wanted.
Yeah. Not step, is it?
So
Yeah.
I thought you were interested in the F value. Okay.
Yeah.
Yeah.
So you can, if you plot it for long enough, then you can probably see it more clearly. So if you go to sort of, 1,000 or something.
I should give that one different color. So one's the X value, one's the Y value. And this is in 3D, so we have another one as well. So I mean, we don't show as much convergence in the sense of like, we're not like trying to actually approximate a value. We're like over time, you might, if you were trying to find a maxima, you would reduce your step size over time. But this is like, you're actually trying to sample the distribution. So after some initial search, then this is just bouncing about and actually bouncing about the amount that is representative of the distribution, right? But if we wanted this to actually do it, like converge on some value, yeah, we could reduce the step size over time, and this should eventually give you a very good approximation of the maxima, right? Okay. So yeah, that just left the integration. There was one problem in here, or two problems. And that was to show how this like we calculated this integral a few different ways using just standard Monte Carlo, and then we did some importance sampling to show the importance sampling was a bit better. And then last of all, we did the Metropolis Hastings version. So let's evaluate these. Yeah. Go back up. Start here. Okay, and then the idea was to now look at this as a function of n and compare the two ways of doing it. So we could see how they compared. Oh, what's going on? What did I do wrong?
I think that this is me trying to add a timer. I think it might have updated the actual thing.
Oh, you pushed
Sorry.
an update to it.
I didn't realize that it was going to push to the actual main. That's my bad.
Thank you. Anyway, that's what. So I played around with this a bit, and the board sampling like had a steeper slope, but it wasn't actually getting that much better. And I just put that down to it's sort of tricky to choose a distribution that importance samples the right way, just a priori. This is not something I've done any of, so I don't know what the tricks are. So what is much more obvious though is if you do the Metropolis Hastings version, and since we're running out of time, I'm just going to skip through this. And then plot the Metropolis Hastings on the same plot. Then yeah, initially it sucks because it takes time to sample the distribution properly at all. But then once you have, then it like jumped down and it was way more accurate. So this was the idea that importance sampling the distribution with the actual distribution, which is what Metropolis Hastings does, you can get a better you can get a much more quicker convergence of the integral. And this sort of illustrates that. And again, so these tend to follow root n, but this one can converge faster than root n, which is cool.
Could I quickly share my screen, Jay?
Yeah, go for it. I'll stop.
Yeah. So what I was doing, which you might have seen, was I was trying to do something with the timer to see how fast these algorithms actually are.
Yeah.
So on this, on the right here is just the plot that we just saw for the different algorithms. I extended it to 10 to the 8 just to see.
Yeah.
And then if we look at the time, MC clearly takes a lot longer. I wasn't even able to run it for 10 to the 8 points.
Which is definitely expected because
Yeah.
of this. So there's definitely some optimization as to go into like this, even choosing the step size and so on, so that your MC rapidly converges and actually does it. Because otherwise, yeah, it's doing a lot of extra work. Also, like, so the Vegas algorithm, which is like the, what do you call it? The proper implementation of this. It does it recursively. So it'll do like 100 samples, then it will use that to have a, suggest a better proposal distribution, and then it will iteratively improve itself, where this is just go out and do 1,000 or whatever, however many points. And yeah, this is also the simplest problem where the uniform actually works really well. And again, higher dimensions, we expect MCMC to be beneficial. In practice, you never do Monte Carlo integration in 1D or 2D. It's the 1D integral, right? They really take over in usefulness at 3 dimensions and higher, I'd say.
Yeah, I'll let you reshare your screen.
There's nothing else to share there. So, and is there any questions or comments on this stuff?
Oh yeah. So for the burn-in for the random walk, I assume there's some more technical prescription for when you should be good in terms of keeping samples rather than throwing them away.
Yeah, I'd say like if you look at say like something to do with the standard deviation of the last n samples that you've stepped, that number should start to converge to something. So if your standard deviation is still changing as you're taking steps, then you're probably not converged. Also, or you could also like we were saying before, we were trying to show that it sort of converges to a value, and so you'd also say like the mean to stabilize. So if you just sort of keep track of those things over time and see when they stop changing, then you're starting to converge.
If you have some less nice distribution, something multimodal, perhaps the mean wouldn't necessarily settle then, right?
Well, it will over some number of samples, and if it isn't, then you're never converged. Like there's some number of samples, and it's going to depend on the distribution where you should walk across enough of the distribution. Otherwise, MCMC is just never going to work. And that may become large, but you should still be able to see at some level some convergence.
Okay.
Yeah, I've thought about this before, and I haven't tried it, but I suspect doing like a Carlo Smirnov test of like the distribution, like a 2-sided one where you see if it's stationary. Could be something, but I don't know how, it would just add time, right? And in practice, it's at least for my purposes, right? You can just make all these plots and just say, well, they look like they're stabilized.
Yeah, I think where like you care more about doing tests that like versus just doing more samples is when each evaluation starts to become like take a long time. So if you've got like complicated likelihood functions that you have to do a bunch of calculations at each step, then you really start to care. Am I doing the optimum number of steps, and am I converging? And then testing when you're doing that is going to be more useful.
So I haven't used Vegas. I can see that you can use it for integration. Can you do it just for sampling as well?
I don't know, but I'm not sure how optimal it is for sampling. I've never used it to sample, just for integrals.
Yeah.
Like what I have done is I have used when I did the previous inference workshop, I did multi-nest, and like so multi-nest is for giving you posterior distributions, but you can use it just to efficiently find maxima in high dimensions, and it's pretty good at that. So if you're not interested in the full distribution, or you can even use it to do integrals, since it's sampling the whole distribution, and it's geared at Bayesian methods, so it calculates the evidence to normalize your distribution. So you can actually use it just to do integrals.
Is that associated with Nest?
No. Multi-nest it's a version of the nested sampling algorithm that handles multiple modes in a better way.
Okay.
So if you're interested in sampling, then you can look that up.
Yeah, okay. Yeah, because I mean, I've used PyMC and I think another one before, but I mean, in practice, it's just easier. It's been easier to just use my own, like Metropolis Hastings, but then it's not always efficient. So,
Mm.
so multi-nest, does it have this? Because I know with PyMC you have to make a, I forget what they call it, some weird way of framing the problem. Do you need to do the same sort of thing in multi-nest?
Multi-nest takes, it's pretty lightweight in like what you have to specify. You get given a unit hypercube, and then you scale that in whichever way you want. If you scale it, well, the way you scale it imposes your prior distribution. If you're doing this as a Bayesian problem, and then you just calculate a likelihood and just return a log likelihood, and you return a likelihood value, and then it does the rest. So it's pretty simple. And yeah, I had an example in the inference notebook where I actually got it working within Colab, which it's not recommended, but at least you can play around with it and see if it's what you would want to do before you actually, spend more time on it. There's a thing called Pi multi-nest. So someone has made it work, callable from Python.
Cool.
All right. I think that's all for today. So thanks for showing up. And Matt is going to do the next workshop in 2 weeks. So we'll post all the recordings for these eventually. So yeah, it'd be good if people do show up live and have a go at some of the exercises, so we can make this a bit of a discussion and sharing. But I know everyone's busy and has stuff to do. Part of the reason I wanted to do this was to guilt myself into learning more Python, and so at least on that side of things, it's worked. So I don't mind playing around and doing things. Okay, any other comments?
Well, I'll fix my changes on the thing.
Yeah, if you fix them and push them, that's great. Like that's the other thing. Like it'd be great if people want to make changes to the notebooks or add to them. Yeah, or if you have any comments, you can add them in and push them, and this will become a more collaborative thing. That'd be awesome. All right. Thanks, everyone. See you in 2 weeks.
Thanks, Jack.
See ya.
See you.
Bye.